Hello everyone and welcome to the next lecture of the NPTEL course Machine Learning for Core Engineering Disciplines. In the last couple of lectures we have looked at how decision trees are a suitable algorithm to solve both regression and classification problems in machine learning, and in particular we saw how a regression based decision tree can be trained, and not only looked at how the prediction is made in case of a regression tree, but also how the architecture of the tree can be decided using the recursive binary splitting approach. In the last lecture we also set up the problem for a classification tree, but we did not get the time to derive the equation, right, that is used for the weights of each decision node in a decision tree. So today's lecture will be devoted to that. So let us go ahead and get started. So the topic is classification using simple decision trees. Right, and what we have discussed so far, that we use the multinomial cross entropy loss, right. So that is minus 1 over n, some I going from 1 to n, and sum over the classes C going from 1 to D, an indicator function which tells you whether the data point actually belongs to class C, times the log of the probability that you predict for the point I, right, to belong to the class C. So because it is a prediction you put a hat on it, right. So this is the multinomial cross entropy loss, which is a generalization of the binary cross entropy loss wherein you have just two classes. So D is equal to 2, right. So this is the index for the classes and D is the total number of classes. And finally, as we discussed, this PIC hat, that is the predicted probability, right, that point I will belong to class C. So this is the loss function that we need to use when we want to train any sort of a multi-class classification ML model. Now to be able to minimize the loss function you need to know, right, what these predicted probabilities are, and we had some discussion, right, in the last class as to how we will proceed to do this minimization. In particular I had mentioned that there are two modifications needed here. The first is that because decision trees make predictions based on the terminal nodes, we need to rewrite this loss function based on the terminal nodes or the regions, right. So if you remember, a decision tree partitions the feature space into regions are k, and we usually assume a total of m regions, right, with a total of m regions, right, and the regions can alternatively be called m terminal nodes or decision nodes. Okay. So if you want to rewrite this loss function in terms of the decision nodes, then this will become minus 1 over n, some k going from 1 to m. So you will just go to every region and then you will look at all the points which belong to that region, and then you will sum over the classes C going from 1 to D, the indicator function which tells you whether the yi really belongs to class C, times log of p hat case C, right. So now we have actually replaced I with k here, because we know that in a decision tree every region makes one prediction, right. So that is why this is happening here. So every region makes only one prediction. So that is why we can just replace it as p k c hat. So this is one change we had to make to the loss function. The other thing is also something I had mentioned last time, that there is a constraint that the probabilities have to satisfy, that is, if you sum over all the classes, right, of the probabilities p k c hat, these should obviously sum to 1, and this constraint can be written as c going from 1 to d summation p hat k c minus 1 equals 0. So, this is the constraint that has to be satisfied, and whenever you have to solve a constrained optimization problem, the method of Lagrangian multipliers is very useful. So, that is what we will do here. We will use the method of Lagrangian multipliers for this optimization. So, we will define the Lagrangian L. So, this L is the Lagrangian here. So, I have used a slightly different L here. So, that is the loss function, right, that we are using, the cross entropy loss, categorical cross entropy loss, plus a Lagrange multiplier times the constraint, and the constraint is c going from 1 to d p hat k c minus 1 equals 0, right, and this is called a Lagrange multiplier. Okay. So, let us substitute the loss function here and see what happens. So, the loss function is minus 1 over n sum k going from 1 to m, sum over all the regions, sum over the points that belong to the kth region, then you sum over the classes, right, and I am changing the dummy variable here, right. Here I was going from here I was using the dummy variable c, I am now switching to the dummy variable L just to make the differentiation easier with respect to p hat k c, and this is something we had done earlier as well. So, inside the summation, as you know, is an indicator function that tells you whether the class is really equal to the Lth class for that data point times the log of the predicted probability, right, for the Lth class in the kth node, plus the lambda times the constraint. So, that is still again, yeah, I will use L equals 1 to d p hat k L minus 1. Okay. So, this is the Lagrangian that we have written down to carry out the constraint optimization. So, let us do the constraint optimization and see what results from this. So, the first thing to do in a constraint optimization is to actually differentiate the Lagrangian versus, right, the independent variable. The independent variables here are p hat k L's, that is the variables we want to determine, right. So, this is 0 at an optimum, and you also, right, differentiate the Lagrangian versus the Lagrange multiplier and set that to 0. So, that is what you typically do in a Lagrangian based optimization. Now, let us focus on the first thing here, right, del L by del p hat k L, and this will be 0 at the optimal values, right, p hat k c. So, that is what is going on here. Okay. So, let us differentiate this term. So, what we get is minus 1 over n sum x I belongs to R k, okay, and sum L going from 1 to d, sorry this. So, what we get here is minus 1 over n sum x I belongs to R k, the indicator function of y I belonging to c times the derivative of the log function. So, that is just 1 over p hat k c, right. So, this is what will happen, the summation will actually disappear, right, over all the regions, because we are differentiating with respect to the probabilities of one particular region, and the second term will simply give lambda, right, and here again only one term will disappear because only one term corresponds to p hat k c and the others go to 0. So, this becomes a simple equation, and then if you rearrange this, what you get is lambda equals 1 over n some xi belongs to Rk, the indicator function of yi belonging to C divided by p hat kc. Okay. So, this is what you get here when you apply the first condition. Now, let us apply the second condition, del L del lambda equal to 0. So, when you do del L del lambda equals 0, and this is quite straightforward, there is no lambda dependence in the first term of the Lagrangian, there is only a lambda dependence of the second term of the Lagrangian, and you will just recover the constraint, right. So, that is sum L going from 1 to d p hat k L equals 1. Okay. So, these are two equations that we have obtained. Let us call this equation 2 and the equation that we obtained earlier as equation 1. Okay. Now, from equation 1 you can actually write an expression for p hat kc. So, p hat kc becomes 1 over n lambda sum xi belongs to Rk I yi equals C, right, and we are able to do this because the region k is fixed here, right. So, we can take it outside the summation, and obviously if you do that, this is the expression you get for p hat kc, and let us call this as equation number 3. So, what I will do now is I will plug equation 3 into equation 2. Right. Why? Because I want to solve, right, I want to get an equation that does not depend on the Lagrange multiplier. So, I am trying to eliminate it in some way. So, I am doing that first by plugging equation 3 into equation 2. So, let us do that and see what happens. So, plugging equation 3 into equation 2, what we get is sum C equals 1 to d, right, and sum xi belongs to Rk times 1 over n lambda of yi equals C is equal to 1. Okay. So, I have simply plugged in this here. So, this is what I get, and then from here I have actually obtained the value of lambda. So, lambda is simply 1 over n times C going from 1 to d sum xi belongs to Rk of yi equals C. Okay. So, this is lambda, and let us call this equation 4, and now we can simply complete the derivation by substituting this value of lambda here back in equation 3. So, using now equation 4 in equation 3, we complete the derivation. Okay. So, we will be able to obtain an expression for p hat kc as we had desired. Okay. So, this becomes if you look closely at the expression, that is 1 over n lambda. So, I am first just going to write 1 over n times whatever is remaining, and then I will divide by lambda. So, everything else other than lambda here, let us first write that. So, that is 1 over n and this summation. So, that is everything else other than lambda in equation 3. So, that is 1 over n sum of xi belongs to Rk, the indicator function of yi equals C. Okay. And then we have to divide by lambda, right, and lambda is what we have here. So, that is 1 over n sum C going from 1 to d sum xi belongs to Rk of the indicator function of yi equals C, and these 1 over n's cancel. So, we get a very nice expression here, and the expression is that p hat kc is sum xi belongs to Rk yi equals C divided by sum C going from 1 to d sum xi belongs to Rk yi equals c. Okay. Now let us try to interpret what these terms mean. So the numerator of this expression means the number of points of class C, right. That is what this indicator will tell you. Every time the yi equals c, the indicator function is 1, and every time that is not true, the indicator is 0. So if you sum over all the points in that region, that is the number of points of class C in region Rk. Okay. So that is this term, and then if you sum over all the possible classes, what do you get? That is simply the total number of points in region Rk. Because you have summed over all the classes. So what do you get now? You get that p hat kc, right, the optimal, right, probability prediction of class C in region K is simply the number of points of class C in region K divided by the total number of points in region Rk. So it is like a majority vote, you just see which class forms the majority class in region K, and then you just predict the probabilities according to that. So larger number of points of class C in region K, that particular class will get a higher probability assigned. So if you want to write it in a slightly simpler manner, you can write that p hat kc is 1 over nRk. So nRk means the number of points in region Rk times the summation of xi belongs to Rk of I yi equals c. Okay, and I am just using this nRk to denote the total number of points in the region Rk. So I hope this makes sense to you, right, how a decision tree works. It just uses the majority prediction, and if you remember for regression it was slightly different. There we were taking the average prediction in a terminal node to be our prediction for the target variable. Here we are predicting the fraction of the points of class C in a terminal node as the prediction of the probability that the point belongs to class C. Okay. So if you want to mathematically formally write this down, the prediction, right, of y hat, right, which is obviously a function of the features x, this is essentially argmax over C for all points belonging to region K of p hat kc. Okay. So what do you do here, right, you sorry, this is not xi but this is just x. So what you do here is you first know, right, what your feature vector is, you see the feature vector which region it lies in, right. So let us say that is region K, then you look at all the probabilities, right, in that region K, and then you pick the class which has the highest probability, right. So this essentially is a mathematical way of saying that we just go ahead with the majority vote, right. So the prediction is the majority vote, right, for all classes considered together. So we consider all the classes together and see which class has got the majority vote, and that is the prediction of the class in that particular region, right. So if you wanted to contrast this with regression, so in contrast, in regression we had minimized the sum of squared errors and not the cross entropy loss, and there you got the prediction y hat of a point x as sum over all the regions ck hat I times I of x belonging to Rk. So that is the indicator function. Essentially you just got the value of this constant in the region in which the point k is lying, and these constants were just given by the average vote. So ck hat was the average of all the y's, right, corresponding to the points lying in region K, and this was derived a couple of lectures ago, and I am just writing this here for your recollection. Alright, so finally we have found out how we can make a prediction, right, for a classification problem, multi-class classification problem in a decision tree using these p hat cases, the probability. So we just take the majority vote. We also saw that p hat kc is simply equal to the fraction of points of class C in region K. So it has a very nice and simple interpretation. Now all this again can be done if you know the architecture of the tree, right. So all this presupposes that you know what the regions are, right. So to determine the regions, one must again adopt the approach of recursive binary splitting, and this was something we had already done for the case of the regression problem. We must again adopt the approach of recursive binary splitting. Okay. So if you remember, what we had done in recursive binary splitting was that at each stage we sort of minimized the error that was being made by splitting the tree into two parts. So we had split the tree into a left part and a right part, and we were trying to minimize the error that was made, and that gave us the combination of the optimal feature and cut point, right. So recall that in regression the recursive binary splitting gives us the optimal feature cut point combination. At each enlargement step of the tree or the growth step of the tree, and we had two regions, essentially one region where xj was less than the cut point and the other region where xj was greater than or equal to the cut point s, right. So this was the cut point and xj was essentially the optimal feature, and this was determined by minimizing the sum of squared errors from the left region, right. So this we can say, let us say, is the left region that originates after splitting the tree, and this is the right region. Okay. And I hope this refreshes your memory as to what exactly is happening when you are doing recursive binary splitting, right. So now in the case of classification, instead of using the sum of squared errors of the left region and the right region, here in classification we use a measure known as node impurity to decide, right, which feature to use to split the tree. To determine the split. Okay. So let us see how this node impurity concept works. Okay. So at each step of tree growth, what you do is, for each available feature cut point combination, so very similar to what we had done earlier, one computes the node impurity and chooses the feature cut point combination that results in the largest node impurity reduction. Okay. Now you can contrast this with what happens in regression. There you are looking at the largest reduction in the sum of squared errors, right. So sum of squared errors must be minimum, right, once you make this particular split. So now let us see how this node impurity is defined, right. So before we can look at, right, which combination of feature and cut point minimizes the node impurity, we need to know how the node impurity is defined. So let us look at some node impurity measures. There are a few of them and I will discuss a couple. One of them is the Gini impurity, okay, and that is defined as G of region Rk is 1 minus sum C going from 1 to D. So sum over all the classes of P hat Kc squared. Okay, so this is how the Gini impurity is defined, and then the other impurity that is used is simply the entropy of the region. So the entropy of the region is defined as H of Rk, right, that is the symbol used for Shannon entropy, that is minus sum C going from 1 to D. So sum over all the classes P hat Kc times log of P hat Kc. Okay. So notice that this is different from the cross entropy we had used earlier, where here we had the true class. Instead at both places you are having the predicted probability. So this is not the cross entropy, this is simply the entropy of the node. Okay. So this signifies, right, what kind of uncertainty there is there in terms of the predictions of the node. So if there is a lot of uncertainty, then these impurity measures are high, right, the entropy measure is high. So you can check, right, take some example cases and see how these numbers will pan out, and we will try to also take up an example in one of the upcoming lectures to solidify these concepts. Now you can look at the gain in the impurity or the reduction in the impurity. So that is defined as the impurity of the parent node minus, and you have to weight this. So you take the number of points in the left region, right, divided by the total number of points, right, times the impurity of the left child node. So remember what is happening here. So you are at a node and then you are trying to split it into two nodes based on the feature cut point combination. So this could be xj less than s, this is if the feature jth feature is greater than or equal to a value s. So here you have nl points, here you have nr points. So that is the number of points in the left child node nl, and nr is the number of points in the right child node. So you have subtracted, right, the impurity of the left child node minus the weighted impurity of the right child node. So nr divided by nl plus nr times the impurity of the right child node, right. So this tells you the information gain that happens or the reduction in the impurity that is happening. So that means you are trying to proceed in the direction of more certainty, right, more information and less entropy. So that is what is happening here. So the tree grows in the direction of reduced impurity, right, which essentially means more certainty, right, leading to okay. So, I hope this makes sense to you. Of course, like I said, we will try to do an example in one of the future lectures. Alright, so now we again come to the point that you can obviously keep on doing this again and again and again till there is just one point in every region, and then your tree will be a perfect tree, right. There will be no error if every point is in one region, but obviously that is an overfit tree. So, when you try to use it on an unseen data set, you are going to fall into a lot of trouble. So, to prevent overfitting, right, that is which happens when the tree is too complex, right, and by too complex I mean it has, we formally defined this earlier, too many regions or terminal nodes, and the extreme case is when every point is its own terminal node. So, to prevent overfitting, which happens when the tree is too complex with too many regions and terminal nodes, we need to carry out regularization, right. And if you remember from a couple of lectures ago, the regularization strategy typically used with decision trees is called cost complexity pruning. So, what happens here is you try to grow the tree as much as possible, right, and then you come back and try to prune out the branches, right, which are not leading to an improved performance. So, you look at sub trees, right, and you try to keep on pruning it till you get a desired trade off between the complexity of the model and the accuracy of the model on an unseen data set, and the regularization parameter, right, let us call it alpha, that is what we called it earlier, which decides how much you penalize the size of the tree, that is something which can be determined by cross validation. So, this brings us to the end of this particular lecture. In today's class we looked at how decision trees can be grown for classification problems. Particularly we minimized the categorical cross entropy loss function using a Lagrange multiplier approach, which ensured the total probability sum to 1, and this showed us that the prediction of every region in a decision tree is simply the majority vote of the class in that region. And we also discussed how you can do recursive binary splitting by maximizing information gain or minimizing the node entropy, node impurity when you split it into two regions, and we also discussed how regularization can again be done using cost complexity pruning. So, what we will do in the next class is we will begin discussing how decision trees can be combined with each other to make better and better predictions, and that will lead us to topics such as bagging, boosting and random forests. Thank you, and I look forward to seeing you next time.